Algebra 2 skills number 16, binomial theorem. Quite a bit to say here. So let's look at the purpose of it. The purpose of the binomial theorem is used to raise a binomial to a power without having to distribute many times. Okay, when you raise a polynomial to a power, especially if that power is 3 or larger, that makes for a lot of distributing and a lot of opportunities for mistakes. So the binomial theorem is a more efficient method than distributing extensively. It makes use of something called Pascal's triangle, which is a nice lesson within itself. To construct Pascal's triangle, every row that you see here begins and ends with a 1. And these non-ones, say take this 2 for example, is the sum of the numbers directly above it. So 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 3 is 6, and so forth. You're going to need those numbers in the binomial theorem. You can memorize them or reconstruct the triangle as needed. You could also use something called combinations that we'll see in one of the examples here in a minute. So here we go, binomial raised to a power. That's when you want to use the binomial theorem. And first thing to say here, especially if there's a 3, it's not that crazy difficult just to write x plus 2 3 times and multiply it out. You have to multiply a few times, but it's not that bad. So if this is sufficiently small, you might just do that instead. But if you choose to use the binomial theorem, you're going to hear several ways from different people. But here's the way I like to show it. First, we're going to set up a template. And this template consists of 4 regions for this problem. The number of regions is 1 more than this exponent. So here we have 4 regions. The first and last region, or big terms here if you want to call it that, has 2 blanks, and every other region has 3 blanks. Okay, so what goes in all those blanks? In the first blank of each region goes the appropriate row of Pascal's triangle, 1, 3, 3, 1. If you go back to Pascal's triangle, which we can go back here and show you, we had that 1, 3, 3, 1 right there. Okay, so whatever row has that exponent in it, that's the row that you're going to need to use. Okay, so it was 1, 3, 3, 1 there. In the second blank in each region, you're going to take the first term and you're going to raise it to our exponent. So x is our first term, x to the third, x to the second, x to the first. I would advise putting anything you're raising to an exponent in parentheses and the exponent on the outside of those parentheses. Notice we're not going to put x to the 0 here. It's counting down, but x to the 0 doesn't do anything, so we're not going to bother writing that down. The missing blank in each region, you're going to put with this 2. Okay, so the 2 goes backwards, to the third, to the second, to the first, and then again, we're not going to fool with 2 to the 0. So the first term goes left to right, the last term goes right to left, and then you just clean it up. So x cubed plus 6x squared plus 12x plus 8. X cubed times 1 is just x cubed. Right here it's 3 times 2 the first. That's 3 times 2 is 6, x squared. 3 times 2 squared is 3 times 4. That's 12x. And then 2 times 2 times 2 here on the end. Notice your variable, x to the third, x to the second, x to the first, and then x to the 0. It counts down. A more difficult example, or actually before we get to that more difficult example, let's look at that combinations idea for just a moment. Now this 3, 0 and 3, 1 and 3, 2, these are called combinations. That's the notation for it. And on a calculator, you're going to say 3 and you're going to find the NCR button in 0 here. Now there's a formula using factorials that you could use, but for the purpose of this video, we'll just use a calculator. So and again, this is if you don't want to use Pascal's triangle or fool with that at all. So 3 comes from the exponent, and you just start with 0 instead of 1, because remember you have 1 more region than you do power. So you start with 0 instead of 1. So 3 comes from this, and then 0 is where you start. So in the calculator, 3 NCR 0, 3 NCR 1, and so forth. And what that does is going to make these same numbers, 1, 3, 3, 1. Okay, then everything else is the same as before. So you could use the combinations instead of Pascal's triangle. A more difficult example, this is the 4th power, so now we need 5 regions. Again, the first and last have 2 blanks, the others have 3. 14641. We won't go back to Pascal's triangle here, but that was the row that had Pascal's triangle. So you have three choices. You could memorize Pascal's triangle, you could reconstruct it, or you could use combinations 4 NCR0, 4 NCR1, 4 NCR2, and so forth. The next blank in each region is going to be the first term raised to the power, so 3x to the fourth, and then you just count down. So 3x to the third, 3x to the second, 3x to the first. I didn't put the 1 that time. And don't put 3x to the 0. It doesn't do anything. Notice the 3x is in parentheses, and the exponent is outside the parentheses. And this other blank is for the negative 5y. We go backwards, the 4 to the third to the second, and so forth. So a lot going on here. The answer is very large numbers, or contains very large numbers. Let's just take the middle one as an example of where this 1350 came from. That is 6 times 3 squared times negative 5 squared. That becomes 1350, and so forth for each of the others. So you might want to pause and make sure you can get those numbers or understand where those numbers come from. Now, several observations. Notice that the x's are counting down. Notice that the y's, we have two variables here, they're counting up. So notice that. Notice also that each term has a degree of 4. Here's x to the fourth. 3 plus 1. Remember, for a degree you add if you have multiple variables. 3 plus 1 is 4. 2 plus 2 is 4, and so forth. Also notice that if you start with a minus, these signs alternate in your answer. And some people teach it that way. They just say instead of setting these pluses up, they'll just alternate from the jump, which is fine, and just not have to fool with a negative written that many times. The reason it does that is if you raise a negative to an even power, that's positive, but negative to an odd power is negative, and it just goes back and forth. And the configuration will be, as long as it's a negative in the middle and non-negative on the end, it will always start with a positive and then go negative and so forth. A third example that involves just a single term. You see this question sometimes, what's the fifth term in the expansion of, say, 3x plus 2 to the seventh? All right, so here, you could use Pascal's triangle if you wanted to. I'm going to use combinations. So the shortcut here, and there's quite a bit to this, the 7 comes from the power. The 4 is 1 less than the term they're asking for. Okay, remember you start with a 0 if you use combinations. So you're going to look at whatever term they're asking for, you're going to go 1 less than that. So 7 NCR4, that'll give you a number. And then you raise the first term to 1 less than what they're asking for. So this power here will always match this. And then 2 to the third, because if you remember, the degree of each term adds to the original exponent. So we need a 3 to add the 4 to make the 7. Okay, so quite a bit going on there. Let me review that once more. 7 comes from the power. 4 is 1 less than what they're asking for. This is the first term raised to that same number here. And this is the last term. 2 is the last term, and it's raised to the power necessary to add to the first power to make the original. Okay, then you multiply that out, and you get this term here. So you might, again, want to pause and take some time to make sure you get that correct term.